All right, so a lot of people that come to the open house always say, wait, what's precalculus? Is precalculus college algebra and trig? Things have been renamed over the years, and precalculus does involve trigonometry. So a lot of people get confused because they're like, should my student take finite trig because that has trig? This has trig in it. We are doing lots of trig in pre-calc. So some of this will be review. We did a little bit of it in Algebra 2, if you guys remember, but some of it will be new. So in this first section, we're talking about angles and their measure. So trigonometry, as you might remember, is tri and measurement, metry, so the measure of three-sided polygons. So originally trigonometry just dealt with triangles in astronomy, surveying, and navigation, but now we use trig for lots and lots of things. Okay, so we use it for sound waves, light rays, planetary orbits, vibrating strings, pendulums, and orbits of atomic particles. So, you know, if you ever ask your math teacher, why are we ever going to need to know this? Like, you need to know trig. Like, it's pretty important. All right, so in trigonometry, an angle is thought of as a ray rotating around its endpoint. The starting position of the ray, or the initial ray, or initial side, is always right here. It's along the positive x-axis. And the final position is going to be the terminal ray. The angle that's trapped between them is going to be whatever angle you're talking about, okay? So you could have things that are more than, you know, previously in trigonometry only dealt with like triangles. So we had everything less than 180 degrees then. So in this case, we can have more than 180 degrees. Maybe we have it going around like this, and we have the initial and then the final meaning like that. Does that make sense? So we can have things up to 360 and even beyond. If something was 720 degrees, what do you think it means it does? We start with our initial ray and it goes where? So what is 720 degrees? What do you think? It goes to full circles, exactly. So we can have bigger than 360 even. Okay, so the standard position of the angle is exactly what we just talked about. You have your initial ray along the positive x-axis, and the terminal ray is somewhere else. So you can have up to 360 and beyond, actually. All right, so that might, you know, you might have some questions about that. Well, isn't it 720 degrees isn't it in the same location as 360 degrees? And they are. So there's some angles that are actually going to be in the same location. Are you guys good over there, Kyle? Yeah. All right, so if we have an angle of 225 degrees, we draw its initial and terminal rays. So the initial ray is going to be here. It's past 180. How much past 180? A little bit. How much is a little bit? 45. So it's directly in between the, it's in the third quadrant, right? Directly in the middle of the third quadrant. Right, so I usually draw a little arc or something to indicate that I've gone around in that direction. All right, and negative 330, for negative angles, we go, instead of, so negative angles, they go clockwise. Okay, so negative angles will go the opposite direction of what we go. So what we were doing for 225 is we were opening up counterclockwise. Does that make sense? So what we're doing now is we're starting with our initial ray, and we're going backwards 330 degrees. Yep, how much will be left? A little bit, 30 degrees. You're very precise today, Alex. Is it the same as 30 degrees? Yes, it's in exactly the same location as 30 degrees, okay? So these are what we call coterminal angles. So angles formed by different rotations that have the same initial and terminal sides. For example, as you can see above, 330 degrees is actually the same initial and terminal sides as 30 degrees, right? So they are the same angle. All right, so find three coterminal angles with an angle of 45 degrees in standard position. So if we have 45 degrees, right, we know that's right here. What we're going to do to get the coterminal angles is we're going to keep adding 360 or subtracting 360. Okay, so we're going to have 45 degrees. But what if I add 360? What would I get? 405. So that's the first coterminal angle. What if I start with 45 and I subtract out 360? What do I get? Yeah, negative 315, right? Does that make sense? All right, you can keep adding and subtracting 360 as needed. Okay, so let's say I take the 405 and I add 360 to it. Well, that's going to be at 765. That would be another coterminal angle. So you keep adding and subtracting 360 degrees. It's basically like saying you're rotating around it one more time, or rotating backwards. All right, so what if we have 180 degrees? Well, 180 degrees is this way. Sorry, sometimes I'm lazy and I don't write the initial ray, right? Because it's kind of implied that it's there, so I just write the final ray. So I'll do that a lot. All right, so 180 degrees. So what's another coterminal angle for that?
540.
Right, you could add 360, and Yaya said 540. That's a good one. Julie, what are you saying? Yeah, you can subtract 360 and get negative 180. Yep.
On the last slide, would we have 770?
Oh, what did I do? 765.
65?
I think it's 765. Is it 765? Because add 60. I think you're thinking 365. 365 days a year. Yeah. This is the bad thing about going from investments to angles. All right. So if you add 360, then we get 900. Could we subtract 360 from the 180? Sure, negative 540. Does this usually happen where we have a positive 540 and a negative 540? No, not usually, right? Positive 30 degrees isn't the same as negative 30 degrees. All right, any others? Add 360 again?
You can add 360 to 900.
360 to 900 and get 1260. That would be a fifth one. So see how you can find all of these different coterminal angles. Okay, not really hard, right? It's pretty easy. All right, so in geometry, you learned that an arc is part of a circle, and the central angle is the angle whose vertex is the center of the circle. So if you remember, we had things like this, where we had a central angle, and then we had the part here, which was our arc. Okay, so we can often talk about the arc length. Now, your book has a different formula for arc length than what I'm going to show you, so I'm going to explain why they do this. All right, so what I will use is the same formula that I used in geometry because I think it makes sense to students, okay? So arc length, let me give you an example. Let's say we have a circle, and we have a radius of 10. What is the circumference of that circle? No. Circumference, what's the formula for circumference?
2 pi r.
Good, 2 pi r. A lot of people say pi r squared still. 2 pi r, right? 2 pi r. So in this case, it's 2 times pi times 10, so it is?
25.
Exactly, 25. So what if I have half of the circle? What's the length of that arc?
10 pi.
10 pi, good. All right, what if I have a fourth of the circle? What's the length?
5 pi.
5 pi. What if I have 3/4?
2 point.
I have 15 pi. Yeah, I wasn't having again. You were thinking of having again, weren't you? So I could have 15 pi. Okay. Does this make sense? Well, what if I have, instead of having that portion of the circle, what if I have 60 degrees in here, and I have just that portion? Can you guys figure out what portion of the circle I have? What fraction of the circle I have? 60 over 360, which is 1/6, right? So we have 1/6 of the circumference. So then the arc length would be 60 over 360 times the circumference. So 1/6 of the circumference, so 10 pi over 3 would be that arc length. Does that make sense? Can you all remember that formula?
No.
Yeah, you're thinking about what fraction you have times the circumference. That's what makes it very, very easy. So for your arc length, that's just going to be whatever fraction of the circle you have, so theta over 360, and then times the circumference, 2 pi r.
Wait, what is the 0?
Theta? Theta is an angle. Yeah.
The angle.
You've seen theta? Seen theta, right? Okay. All right. So I said I always recommend that students find the total circumference of the circle and then think about what portion of the circle they have, what fraction they have. This makes memorization much easier. So there is a formula in the book that says arc length is equal to r times theta. They actually use s for arc length, which I think is silly. I use L for arc length. When the angle is in radians. So this is only when your angle is in radians, okay? Yes. I know, the clock is off. It doesn't work. So don't stare at the clock. It's broken. All right. So this is only when our angle is in radians, which we haven't talked about yet. Okay, so the convenience of using the other formula is I think it makes more sense. And that formula will work even if it's in radians, so I'll adjust when we learn what radians is, okay? So number 1. So it says a circle has radius of 6 inches. Find the length of the arc intersected by a central angle of 240 degrees. Okay, so we have a radius of 6 inches. So if I'm finding the total circumference, I have 2 times pi times 6. So I get 12 pi. So if I want to find my arc length, I say, oh, I have 240 degrees out of 360 degrees multiplied by that circumference. So 240 over 360 reduces down to 2/3. So 2 times 12 is 24 divided by 3, so 8. So we get 8 pi. What would my units be?
Radians.
Inches. You're just waiting on those radians, aren't you? All right, number 2. So an arc in a circle has an arc length of 200 pi. So this is kind of going the opposite way. This is our L. And the measure of the central angle is 60 degrees. Find the diameter of the circle. Okay, so we're going backwards. So we know that the length is going to be whatever theta over 360 is times the circumference, 2 pi r. But we don't know what r is. We know our length is 200 pi, and we have a sixth of the circle, right, 60 over 360.
How can you use pi d?
Hmm?
Have it easier as integers, right?
You can, yeah. If you want to use pi d, do you see what she's saying? Like use the alternate form for the circumference. So we have 2 pi times r. All right, so I'm going to kind of simplify. So 60 over 360 is 1/6, but times 2 is going to be 2/6, which is 1/3. So I'm going to have 1/3 pi r equals 200 pi. And if you have pi on both sides, you can actually divide by pi. So you get 200 equals 1/3 r. So what's r? It's big. 600, yeah. It's kind of a weird one to think about because the angle is pretty small, 6 degrees. So we get 600. So our diameter then is twice that. So we get 1,200 inches. All right, so a lot of times if you're covering a very, very large distance, so let's say you're traveling in a boat and you're the one driving the boat, captain, or a plane, so Alex, if you're ever, traveling by plane, being off by a little tiny bit can totally mess you up and you can be totally lost for a long time, right? So being off by just a fraction of a degree and traveling for a long distance, you could not end up even close to where you need to be. Or you could run out of gas before you get to the place you want to be, right? So it's important. All right, I know. All right, so a lot of things like naval navigation uses something called degrees, minutes, and seconds. Okay, and it's very similar to time. So if you think about an hour, how many minutes are in an hour? 60. How many seconds are in a minute? 60. So how many seconds are in an hour? Not 360. 60 times 60, which is 3,600, right? The same thing applies for degrees. Okay, so in a single degree, there are 3,600 little marks, 3,600 seconds in it. Does that make sense? So in a single degree, you can break it up into 3,600 little portions of that degree. See how important that would be? It's very, very, very precise.
In a single degree, so 1 degree.
In a single degree, yeah. Because a degree is made up of 60 minutes, and every minute is made up of 60 seconds. Okay?
Okay, so there are 360.
3,600 seconds in a single degree. All right, so this is a very, very, very precise way of measuring. Okay, so we call this DMS notation, or degree, minute, second notation. All right, so it's a little bit weird. So this first one, so it says convert 42.425 degrees into degrees, minutes, seconds. Okay, so let's break it up. Degrees, minutes, seconds. Okay, the degrees. How many full degrees do we have? We have 42 full degrees, right? So we're going to start out with 42. Now it says how many minutes do we have? So what we're doing is we say, well, we have that fraction, 0.425, and we want to divide by 1 over 60. We want to find out how many minutes go into that number. Okay, dividing by 1 over 60 is really the same as multiplying by 60, right? So if that's easier for you. So we go ahead and we do that. So we do 0.425. You multiply by 60 or divide by 1 over 60. And what do we get? 25.5. So how many full minutes do we have? 25. Okay, we write that with a foot mark. You know what I mean by that? Like 6 feet too. Little foot mark. All right, but then we have a portion. We have this 0.5, which is 0.5 of a minute. Think about time. 0.5 of a minute. Half of a minute. How many seconds is that?
13.
It's 30 seconds, right? You're very precise. All right, so what we're going to do is we're going to take that 0.5. It's already been multiplied. We've already done the like 1 over 60 thing one time. We're doing it again. It's like the 3600. So we're doing divide by 1 over 60. So we get 30. Okay, that's going to be our inches. Or not inches, jeez. That's going to be our seconds. Use an inch mark for it. Yes? Because we've actually already done that once. Does that make sense? You've done the 1 over 60 already. That was a portion from that. And now you do it again. Yeah, it's kind of weird. You don't multiply like 1 over 3600. A lot of people think that. Okay, so what we end up getting is 42 degrees, 25 minutes, and 30 seconds. Okay, do we need to see another one of those? The other class needed to see another one. Let's do another one. So let's say we have 58.875. All right, so we're first going to talk about degrees, then minutes, then seconds. So degrees, how many full degrees? 58, we're good there. Now we take that 0.875 and we divide by 1 over 60, which is the same as multiplying by 60. 52.5. Should have made it something more interesting. So we get 52 full minutes, but we now have to take that 0.5 of a minute and convert it into seconds. So it's already in minutes. So going to seconds, we just do divide by 1 over 60 or multiply by 60. So we get 30. So it's 58 degrees, 52 minutes, and 30 seconds. When I talk about what?
Arc minutes or arc seconds.
Probably, yeah. I don't know if I've ever heard it called arc minutes, but that would be the same, yeah. All right, convert. So going backwards. So let's say I want to convert 35 degrees, 12 minutes, and 36 seconds into degrees. Okay, so what I'm going to do is I'm going to take it's clearly 35 point something, right? So I take my 35, and I add it to the 12 minutes needs to be 12 out of how many minutes are in? Yeah, there's 60. So what we do is we do 12 out of 60. So we have 12 minutes out of a total of 60. But then we have 36 out of what? 1 over 60 times 1 over 60. So Catherine, that's what you're asking about. That's when you do it twice. Does it make sense? Okay, so we're going to find each of those. So I have 35 plus 12 over 60 plus 36, basically over 3,600 if you want to write it that way. So we get 35.21 degrees. That's our answer. Yep. All right, one thing that will also be different about nautical navigation is we will sometimes refer to nautical miles instead of miles. This is one thing I did not even understand until I started teaching. I was like, what are nautical miles? Are they just miles just on sea? They're not. It really has nothing to do with a mile. So since the Earth is approximately spherical, this picture is not the best either. So since we have a sphere, what we do is we consider a nautical mile to be 1 minute of the Earth's circumference at the equator. So what we're going to do is we take, so what was 1 minute? 1 out of 60 of a degree, right, of that Earth's circumference. Okay, so we take 1 minute of the Earth's circumference. That ends up being nautical miles. So we're going to do this one time, and then you're just going to have the conversion factor, and I'll give you the conversion factor when we need it. So it says find the way we convert from nautical miles to statute miles by using the fact, so statute miles is just regular miles, by using the fact that Earth's radius is 3,956 statute miles. Okay, so we're going to find the circumference of the Earth. So you can find 7,912 pi, or if you multiply it out, you get 24,856.281. Okay, and you can store that if you need it, just in case. All right, and what we're doing is we're finding 1 minute of 1 degree. Okay, so that's the whole circumference. So if I was finding how much 1 degree is, I take that number. How many degrees are there in the circumference? Going all the way around, how many degrees do I have? 360. So I'm going to have, gosh, how do I want to do this? I'm going to divide by 360. So let's put it on the bottom, because I want to find for 1 single degree. Oh, is that what I want to do? I don't want to write it like this. Okay, let's divide by 360 degrees. So we're finding how many miles there are per 1 degree. Divide by 360. Miles for each degree. But we don't want for 1 degree, we want for 1 minute of 1 degree. So the last thing we need to do is we need to multiply by 1/60. The definition was, so if you go back here, it says, what it is you find the entire Earth's circumference, and you find a single minute of Earth's circumference. That ends up being a mile. So it's like you divide this whole circumference into 360 parts, right, for the 360 degrees, but we don't want degrees, we want minutes. So now you divide those into 60 more pieces. Okay, so we're dividing by 60 again. Uh-oh, I don't think this is the right number. No, I'm scared. So I get 1.15 1. Oh yeah, that's right, okay. So this is the number of, let me think about it. Miles equals number of 1 nautical mile. So we just found 1 nautical mile, I think. Let me make sure that I don't have that backwards. All right, so that's our conversion factor. 1 like mile on land ends up being equivalent to 1.151 miles on land. It ends up being equivalent to 1 nautical mile. So take that number on your calculator and do 1 over it, right? And you get like 0.87 around there. So that's the other one. So 0.87 nautical miles equals 1 statute mile. Okay, so I'll give you those conversion factors if you ever have to use them, so we don't have to go through that. So that's where it comes from. It doesn't really make sense. It's like, wait, why do we use that for miles? That's just a random measurement. But it does make navigation easier using like that standard 1 for 1 minute. All right. So it says we do not always want to use rounded answers when dealing with degrees. So in many occupations, we need our angles to be as precise as possible. So this is why we use radians. So you guys remember radians a little bit from last year? Radians? Do you remember what it was? All right.
The 2 pi is 360 and pi.
Right, 2 pi is the same as 360 degrees, pi is the same as 180. Okay, so what a radian measure is if you take a unit circle, so 1 unit in radius, and you talk about the length of the whole circle. What's the length all the way around the circle? What do we call that? Circumference. What's the circumference of the circle?
2 pi.
So if I want to refer to moving a certain distance around the circle, so if I want to talk about tire, how much it's moving, what I do is I use radians, okay? Yes, we're going to do the unit circle. It's on our next page. All right, so it says in simpler terms, radian measure is the way to describe, guys, an angle measure using arc length on a circle of radius 1. So the circumference is 2 pi, so a radian measure of 360 degrees ends up being 2 pi radians. No, we're going to see it a lot, actually. Unit circle is super important.
Oh, no. You got any new circles with again?
Yeah. Seriously. Did I tell you, like, my roommate in college, she said her math teacher thought the unit circle was so important. Did I tell you this story?
Don't tell us.
She told me that her math teacher loved the unit circle so much that she told her entire class that she had a tattoo of it on her rear end. I do not have a tattoo of the unit circle anywhere. It's important, but I don't go to extremes like that. So, yeah. Yeah, if you put a tattoo right on your arm. All right. So if we have 180 degrees, so going halfway around then. So the full way around was 2 pi. So going halfway around is going to be what? Pi, you got it. So that's going to be pi radians. 90 degrees is going to be half of that, so pi over 2. And 45 degrees is going to be half of that. So if I have 1/2 pi, and half of that is going to be 1/4 pi, right? So pi over 4, exactly. So I really should write radians, radians. Right, if you don't write radians, radians actually the non-unit. So we don't have to write it.
That's so great.
All right, how about 30 degrees? Over here was 180. Here's 30 degrees. What fraction of 30 is 180? It's a sixth of it. So it's pi over 6. 270? 3 pi over 2, because it's going to be going around. 1 pi and another half of a pi. All right, and then 330? Ah, you guys are good. You just memorized this? You just remembered it? All right, what could you do if you didn't know? How do we convert? Do you remember the formula?
Wait, is it like the...
So our formula to convert, if I have 330 degrees and I didn't know how to make that 11 pi over 6, what you do is you put degrees on the bottom. Shh, guys. Degrees on the bottom, radians on top. So I put 180 degrees is the same as pi radians. And I reduce it. So I say 330 divided by 180. So I know they're at least divisible by 10. So then I have 33 over 18 pi, and that goes down further. That's divisible by 3.
11 over 6.
So you get 11 pi over 6. Yep. So you could do it that way, right? But that would be very time consuming. We really should memorize this. Really, because you're going to do it a lot in pre-calc. It's like 3 chapters worth. It's not just a section in pre-calc. So it's very important. All right, so let's fill in our radian measures. So we have 0, but also 2 pi, right? So 0 is indicating that our angle, our initial and terminal, are exactly at the same spot. All right, and 360 means that you've opened it up and it's gone all the way around. All right, and then 180 was pi, 90 was pi over 2, 45 was pi over 4. So we have some of them. 30 we said was pi over 6 because 30 is 1/6 of 180. Likewise, 60, what fraction is it when we compare it to 180? It's a third, right? 1/3 of 180. So this ends up being pi over 3. And then the second quadrant, you can use what you know from the first quadrant. So 120 is double which angle? It's double whatever 60 was, so this has to be 2 pi over 3. And 150, is there anything that we can use to find it? Well, we know 30 degrees was pi over 6, so what does 150 have to be? 5 of those, 5 pi over 6. You could also think it's, pi over 6 away from getting to pi, so you could do pi minus pi over 6. 1 minus 1/6. How about 135? What do we think? 3 pi over 4, because it's 3 of those 45s. All right, and we continue to fill in. So I'll do these. 7 pi over 6. This one's going to be, what do you think? It's pi over 4 past pi. So if you do 1 plus 1/4, 5 pi over 4. This one's going to be pi over 3 past pi. So 1 plus 1/3 is 4 pi over 3. This one we said was 3 pi over 2. 300 is 60 degrees away from 360, so we could start with 2 pi and subtract out 1 pi over 3. So 2 minus 1/3 is going to be 6 minus 1, which is 5 pi over 3. This one's going to be 7 pi over 4, because it's pi over 4 away from being at 2 pi. And this one's going to be 11 pi over 6. So there was a shortcut that I taught you just for your unit circle quiz. Do you guys remember how to do it? So the shortcut is you skip the 45s for the first one. So skip the center of the 4 quadrants. Skip those ones. And everything else is going to get a pi over 6. So as I'm going to go through, this is going to be 1 of the pi over 6s. This will be 2 of the pi over 6s. This will be 3 of the pi over 6s. This will be 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, skip it, 8 pi over 6, 9 pi over 6, 10 pi over 6, skip it, 11 pi over 6, 12 pi over 6. That's also 0. Right? And then you just reduce. Do they work out to be the same thing? Yeah, 8 over 6 is 4/3, right? It works out the same. And then you go through and you do the pi over 4. So you're like, okay, I have 1 of the pi over 4s, 2 of the pi over 4s, 3 of the pi over 4s. You always have to hit the quadrantal angles, the ones that are in the axes. All right, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. So see how it works? Go all the way around. Make sense? All righty. So the radian to degree conversion. So if you have radians and you want to switch to degrees, you put radians on the bottom, degrees on top. So it's 180 over pi. But to degrees, radians would be pi over 180. So I just do it just like chemistry conversions. So if I had pi over 9, I put pi on the bottom, 180 on the top, and the pi's reduce out. So 180 over 9 is going to be 20, so it's 20 degrees. All right, same thing for this one. So I do 180 over pi. So the pi's reduce out. So 180 and 5, how do they reduce? 36, is that right? Yeah. So 36 times 3 is going to be 108. You could use a calculator too. All right, and then 5 pi, 180 over pi, so you end up getting 900 degrees. The pi's cancel, 5 times 180. Emerson. All right, so that was converting from radians to degrees. It's the same thing for degrees to radians, so it's just flipped, right? So if you have degrees, that means you want degrees to be on the bottom, so 180 on the bottom and pi on top. So we get 150 over 180 pi, which does reduce. So 15 over 18, divide by 3, so 5 over 6 pi. So 5 pi over 6. You guys remember all this?
We're getting there.
You're getting there? Going kind of speedily. All right, so what about 330 over 180? How's that reduce? Anybody got it? Oh, that's one we had earlier, isn't that 11 pi over 6? All right, and then 540. Yeah, that one's 3 pi. Good. So you just reduce everything down. All right, is that it? Yep. All right. So you pass out your homework.